like this, which I explicitly warned you about. Not true, right? Not true.
That x equals 0.
Yeah, x equals 0, for example, satisfies this one, but not that one, okay? I think I mentioned this in the context of absolute values, where you also just can't throw absolute values on both sides of something, okay? And you should, you know, if you made this mistake in your homework, you should think about why you made this mistake. And the only reason why you could have made this mistake is because you weren't thinking, right? You were doing things just because they seemed right or something, right? And not thinking about what you're doing. Okay, so lots and lots of issues. So, you know, we may go over this again a little bit later because you need to know how to do these inequalities. They're incredibly important. But today we're going to finish up this section, including the binomial theorem. So if you remember what we did last time, we discussed the choose function. That's a k. Which is the number of ways to choose k socks out of a drawer full of n socks. Okay, and again, that's not something I'm going to prove now, and you'll see this maybe in a basic class on probability. But we have a use for this. And that's known as the binomial theorem, which is a very important theorem, but more important than the theorem itself, because a lot of you have probably seen it. If you haven't, no problem, we'll get it. But more important than that is the proof, which is a bit complicated, and it involves, as usual, some basic techniques that you need to know when you're doing mathematics. Okay, so last time we proved this little lemma, and again, it was nothing but just basic algebra, right? And knowing what your definitions are. And the first thing I want to say about this is it gives you a basic computational way to figure out what these guys are. This is really you could make this sort of your iterative definition, right? If you wanted to. Because what it does is it tells you how to get the n plus first ones out of the nth ones, right? And that's exactly the way iterative things work. But this is actually something that we proved. Our definition was not iterative. It's right there. But this will give you a real easy way to calculate this. In particular, these are very, very big, right? Factorials are, you know, among the fastest growing things. Right? They grow very quickly because you're multiplying by bigger and bigger and bigger numbers. They grow faster than exponentials, for example. So, but you also have this stuff here in the bottom, which has a mitigating effect on the size, right? Because you're also dividing by some factorials. So these numbers are not as big as factorials, right? And so this will help you get away from having to calculate monstrous numbers and then divide by monstrous numbers to get smaller numbers. Okay, so those of you who are interested in computer science and computing, okay, you should recognize that this is a good thing, right? In terms of cost of computing. Okay, so let's see how this makes our lives easier. Okay, so that's a 1. And 1 is the same as 0, choose 0, right? The number of ways you can choose nothing from nothing, well, there's one way, and that's to choose nothing. Okay, now this is 1, 0. That's the number of ways to choose no socks if you have one sock, okay, which you might as well do, right? Because it's more embarrassing to have no socks than one sock than no socks, I guess, okay? But that would be the other alternative, to choose one sock from one sock, and there's one way to do that. And now 2, 0. Well, what are we going to get as we make this little chart? What are we going to get always over here? 1, because that's the number of ways to choose 0 from however many you got, okay? And what are we always going to get over here? I want to move that over a little farther, make it more like a triangle. Yeah, over here we're always going to get n choose n, which now is going to be 2 choose 2, and that's a 1. And now this tells us, this formula tells us how we figure out what's in here, because this is going to be 2 choose 1, so we bump up to the previous n, which is 1. We look at the k minus first one and the kth one, and then we add them. Okay, so here's our 1 slot. The k minus first one is 0, and the kth one is 1, so it tells us we have to add those two guys. Gets us a 2. Okay, so this is 2 choose 1. Okay, well now let's just fill this in, right? 3 choose 0 is 1, and now we want to do, I want to move that over a little farther. And now I want to do 3 choose 1, but again it tells me that I look at this, I look at that, and I add them. Okay, so that's just a 3. So that's 3 choose 1. And then for this one, I add these two. So it's 3 choose 2. And then over here, of course, 3 choose 3 is going to always be 1. Okay, so what's the next row going to be? Always starts with 4. So this is the row that has 4 choose k in it, right? 1, 4, 6, 4, 1. And then 1, 5, 10, 10, 5, 1. Now, what is it that you see here from side to side happening? Symmetry. This is a symmetry that I pointed out quite a bit ago, right? That is, you have symmetry down below here. And as k marches up, n minus k marches down at the same rate, right? So you get the exact same numbers here as you do over here, you just get them in reverse order. And so there you see that this entire thing is symmetric, right? So it's extremely rapid to calculate any of these things. Or it's certainly much faster than trying to do these huge factorials, right? I mean, already here we're up to 5 factorial. But the numbers down there are much, much smaller. Okay, so questions about that? That's called Pascal's triangle. Okay, well, why do you care about these numbers? Okay, well, because they're connected, they actually show up everywhere. Okay, you can imagine that this is really sort of a basic idea that you know, choosing some number out of some other set, right? This is something that just happens all the time. And the first place where it occurs is in something called the binomial theorem. So for A and B an element of R and N an element of N, so here's the binomial part. Binomial, bi is 2, as you know. Nomial is what? Number or something, right? Binomial, so it's 2 things being added and raised to this power. And that is the sum from k equals 0 to n of n choose k, a to the k, b to the n minus k. You will know that when you come back from break. You won't know it at your peril. But it's really not that hard to remember. The important elements here are, well, of course, that side you'll remember. The important elements are the summation. Summation starts from 0 and goes up to n, okay? And it's the sum over k. And then you get the choose function. And then what about this stuff here? Well, these are doing the counting in the same way that you count as you go across here, right? Because A, the power of A in the summation starts from 0, and each term it bumps up by 1 until you get to where? A to the n will be the power of A in the last term. Whereas with B, where does B start in the first term? did I say, what did I say about A? Did I get that right?
Yeah, you said it starts at 0.
Yeah, okay. Somehow okay, anyway, because actually the point is it doesn't matter which order. I'll say something about that in a minute. Yes. So here, right, you're starting with n, and then what's happening? Each time you're dropping down by 1 until you get to b to the 0, which is 1, right? Okay. So now note that you could put an n minus k there and a k there. It's the same symmetry, right? Because you can replace k by n minus k there because of the symmetry from the formula. So it doesn't matter which of those you pick when you're doing a proof involving the binomial theorem. All right? You can reverse those. So that's one thing you don't have to remember. Of course, it might matter actually whether you're choosing the 0th and first term, for example, versus the n minus first term and the nth term, and some examples we'll do later. But the point is, the order of this doesn't matter. And if you even somehow forgot and put a k minus 1 in there, it wouldn't matter. N minus k in there, it wouldn't matter. Okay. So let's check this. We're going to do this by induction anyway, so let's start by checking the base case, right? So a plus b to the 1, okay, let's just write it out. That's the sum from k equals 0 to 1 of n choose k, a to the k, b to the n minus k. So how many terms are in this sum?
2.
Why should there only be 2 terms in this sum?
Because there's only 2 integers.
Yeah, there's only 2 terms in this sum, right? Because you're raising to the first power. So you know there've got to just be 2, and that tells you that, yes, in fact, there are 2. There's the 0th term and the first term. Okay? So then we're going to start with n choose 0, because that's the k equals 0th term. And this is then a to the 0, b to the, okay, let's go ahead and make my replacement here, actually, sorry, 1. Okay, and this is then b to the 1 minus 0 plus 1 choose 1, 1 a to the, this is now the k equal first term first plus b to the 1 minus 1.
Shouldn't it be times, not plus?
Times, yes. Which is a really complicated way to write what? Yeah, b plus a. And you know multiplication is commutative, so it's right. Okay, so I mean, this isn't really the most useful way to use a binomial theorem. Let's try something slightly harder. A plus b squared. Okay, so let's just start, without writing out the sum, let's just start writing things out. Okay, so we're going to have 2 choose 0. A to the 0, b to the 2, plus 2 choose 1. Okay, so now let's actually just start using our terms here, right? So this is 1. So 2 choose 1. Now we can come over to Pascal's triangle and say, okay, here it is. This is 2. And then we've got a to the 1, b to the 1. Plus 2 choose 2, which you know is 1. And then we've got a to the 2, b to the 0. Which looks like b squared plus 2ab plus a squared. Which is, in fact, a plus b squared. Okay, and now you see, you can start to write things down really easily, right? Okay, so if we look at a plus b cubed, that's going to be equal to a cubed plus 3a squared b plus 3ab squared plus b cubed. Okay, and so again, notice what's happening here, right? The powers of a and b always add up to 3. And the powers of a are dropping, and the powers of b are going up. And then the coefficients are just drawn from Pascal's triangle. So if you need to do a binomial, and you're going to have to do those occasionally in your life, unless you stop doing math right now, and drop this course, okay? Yeah, so it's straightforward to do, okay? Now, let's go ahead and prove it. So we're going to prove it by induction. And so my base case is right here. So we're going to assume that a plus b to the n equals the sum from k equals 0 to n of n choose k